for doing this IR thermography, let us begin with a problem, okay, which I am going to pose over here, which is the problem from our research group, okay, where we will talk about the significance of the problem and why a new measurement technique was necessary for this. Okay. So, let us take the case as you can see on this in this PowerPoint presentation, that in our group we needed to measure the temperature, okay, of a levitated droplet. That circle that I have marked, inside that circle there is a green colored droplet that you can see. So, that green colored droplet basically is a levitated droplet, that means a droplet which is hanging from free space, okay, under acoustic pressure. So, the main purpose of this exercise was how to measure what is the temperature inside or on the surface of this levitated droplet, right. So, and this droplet was of the order of say 500 microns. Okay. We needed to know the temperature because you know using a lot of there could be a lot of things, but we really needed to know because this droplet was also heated by a laser, and we needed to know the temperature of the levitated droplet. Now, this is looks like a very challenging task because your TLC will not work over here, because you do not want to change the properties of the droplet, okay, and the temperature range can be quite high. So, it is more than the range of the TLCs in certain cases. So, the main idea was to devise a measurement technology by which we can actually measure the surface temperature of such a droplet. Now, in this particular case, a measurement technique like IR thermography, which is non-intrusive, emission based, that can come in very handy. Okay. So, that is what we are going to describe in the. So, just to give a prelude that in complicated situations like this, you need a new technique which is called IR thermography. So, this is for example, what is the temperature that we measured. If you look at it, this is from our experimental data from my research group, and you can see that we have a sufficiently fast acquisition. From 0 to 8 seconds you have quite a lot of images. You have a sufficiently good resolutions on the temperature, we can measure from 60 to 19 degrees, correct. Okay. Now, this is not possible with the TLC because the temperature band is usually very small, right, to begin with. Okay. So, you can see how the temperature starts, then how it grows, how it kind of equilibrates, and this is the droplet getting flattened and things like that. So, it is a global technique once again. You can measure the surface temperature of the droplet, but you have to have some kind of a technique which measures this, right. So, once again IR thermography comes in very handy in this particular case. Basically IR thermography requires an IR camera, infrared camera. Okay. So, that is the camera that you use basically to monitor the surface temperatures. Okay. Now, other examples, this is from our group. Okay. There could be other examples, like for example, this is a wind tunnel experiment. You want to measure the local heat transfer between a plate finned heat exchanger, okay, using infrared thermography. That is one other kind of measurement that you might want to measure. Okay. This is for example, in the steady state temperature distribution on the plate fin surface. So, you can see the temperatures, right, all these places, these are temperatures. You can see the linking between the two which is happening because of the flow, right. So, there is a fore and aft asymmetry of the temperatures, correct. Okay. You can see the wake patterns very clearly, right, that how each of these holes are dominating each other, correct. Is not that so? Okay. So, the steady state temperature distribution on the plate fin surface in time, staggered arrangement, there are lots of arrangement, all of these things done using IR thermography. All right. So, IR thermography, you are able to see this temperature distributions, okay, across different directions using this particular technique. Got it? So, another thing could be a transient thermography measurement technique for simultaneous film cooling. Film cooling is what we use in the gas turbine blades, right. So, for film cooling, okay, one uses this infrared camera, and that the film cooling setup is right here, and you can use it in a wind tunnel and you can measure what is the temperature. Okay, non-intrusive, and it does not require any probes, give you the field measurement, right. Can be used at very high temperature situations also, where thermochromic liquid crystals may not be the right candidate to use. Okay. So, giving in mind that all these applications like which involves turbines, which involves simple droplets, okay, which involves fins in heat exchangers, IR thermography is a very attractive technique to use, correct. Okay. And this is, for example, this is the film cooling holes, and you can see that how the holes, what is the temperature distribution across the holes for the different values of your momentum fluxes. Okay. That means the film cooling, there is a hole through which you actually inject fluid, and then there is a cross stream. Okay. So, depending on the ratio of the two, you get all kinds of temperature profiles over here. Okay. So, all these things are very attractive. You can get measurements with this kind of accuracy, with this kind of resolution, which makes it a very attractive tool, right, to use in our measurements, because these are the measurements which will help you to calculate the Nusselt number, right. These are the measurements which will enable you to calculate the heat transfer coefficient H, right. So, these are important things, because this is how you protect a gas turbine blade. If you do not know the Nusselt number properly, or you do not know the temperature distribution, your blade will basically burn out, right. You have to protect your blades, and gas turbines are expensive, okay, expensive propositions. Okay. So, there are a lot of things that you have to that uses the infrared technologies. Okay. There is this thermal science which we are doing. Okay. There is some inspection and routine things which we are not going to cover, okay. And there are other applications as well that uses this kind of a technique. So, what is the theory of thermography over here, because that is the most important part. We have shown you a lot of examples where it can be used. Now, let us look at what is the difference, okay. How do we actually measure it? The electromagnetic spectrum, as we already know, is divided arbitrarily into a number of wavelength regions called bands, right. So, you can see bands 1, 2, 3, 4, 5, 6, right. Out of this, one is basically the X-ray band, right, X-ray, which is of the tens of nanometers, right. Then the second band is your UV band, which is of the order of, as you can see, 100 nanometer to close to, it is centered around 100 nanometer. Third is basically you go to the visible region, that is where we can see, our human eyes can see, you and me and everybody else. Okay. Then you go to the IR, and IR is a very large band. Okay. It starts all the way up to approximately close to 1 micron, goes up and up, and you can see that it ends somewhere there. Okay. Then comes the band of the microwaves, okay, and the sixth is the radio waves. Okay. So, this is the full electromagnetic spectrum, with the last one extending up to kilometer, right. So, this is based on the wavelength, correct. Okay. So, IR thermography basically deals with this. Anywhere between 2 micron to 13 micron is a good candidate, is a good IR band. Okay. This is where we take our measurements, got it. So, that is why it is called IR thermography, that means which uses the IR band. So, thermography makes use of the infrared spectral band. Okay. So, at short wavelength, the boundary lies at the limit of visual perception, and in the deep red. At long wavelength, it merges with the microwave radio wavelengths, and it is in the millimeter range. The infrared band is further subdivided into 4 smaller bands. Okay. They are called near infrared, which is 0.75 to 3 micron. This is some of the tunable diode laser based spectroscopies are carried out in this range, 0.75 to about 3 micron. The middle infrared, which is between 3 to 6 microns, which is the middle band. Far infrared 6 to 15 microns, and extreme infrared 15 to hundreds of micron. Okay. Although the wavelengths are given in microns, the other units can be used. It can be nanometers, it can be angstrom. Okay. The relationship is there. 10,000 angstrom equal to 1000 nanometers equal to 1 micron, right. This is the common conversion factor, right. So, you should remember that there are 4 infrared bands: near, middle, far, extreme, right, progressively as you increase the wavelength. So, infrared is by far is a very long spectrum, okay, before you go to the radio waves and the microwaves and things like that. Okay. So, let us look at the simple problem of blackbody radiation. So, a blackbody is defined as an object which absorbs all radiation that impinges on it at all wavelengths, right, at any wavelength. So, the Kirchhoff's law, which is basically Gustav Robert Kirchhoff, okay, states that a body capable of absorbing all radiation at any wavelength is equally capable in emission of radiation. Got it? That was the Kirchhoff's law. Okay. So, the construction, why we are talking about the black body, we will see in a little bit. The construction of a black body source is very simple. The radiation characteristics, you know that you have an isothermal cavity, right, with a small aperture, okay, is made of an opaque absorbing materials like the properties of a black body. So, normally we paint it with sooty color. Okay, a practical application will be the, consist of a box that is light tight, except there is an aperture on one of the side. Okay, and any radiation that enters the hole is scattered and absorbed by repeated reflections, okay, within that box. Okay, so the blackness which is obtained at the aperture is nearly equal to that of a black body and is almost perfect for all wavelengths. So this is how you construct a black body. By providing such an isothermal cavity with a suitable heater, it becomes what is called a cavity radiator, right. An isothermal cavity, when it is heated to a uniform temperature, generates this black body radiation, the characteristics of which are determined solely by the temperature of the cavity. Such cavity radiators, okay, are commonly used as sources of radiation in temperature reference standards, okay, for calibrating thermographic equipments. Okay. So, you need a black body, okay, to basically calibrate. Now, Max Planck, we all know, one of the 4 founding fathers of the quantum mechanics, right, was able to explain the spectral distribution of a black body radiation, okay, by means of the following formula. Okay. So, H was the Planck's constant, K was the Boltzmann constant, T was the absolute temperature, lambda is the wavelength, C is the velocity of light. This is W alpha b, lambda b is the black body spectral radiant emittance at wavelength lambda. Okay. You do not have to know a lot of radiation physics at this particular point, but you know that Planck was able to describe the spectral distribution of the radiation. Okay. So, when it is plotted graphically for various temperatures, produces a family of curves, essentially, that is what the Planck curve is, right. So, the spectral emittance is 0 at lambda equal to 0, then it increases rapidly to a maximum, which is called lambda max, and after that it approaches 0 at very long wavelengths. Okay. Higher the temperature, shorter is the wavelength at which the maximum occurs. So, this is basically the black body spectral radiance emittance, okay, radiant emittance according to the Planck's law. So, this is plotted for the spectral radiant emittance and the wavelength, right. So, you can see that it is 0, then it peaks up, okay, and it peaks at a shorter wavelength as you increase the temperature. So, there is a shift like this, right, okay, in the maximum, and it again starts to become 0 at longer wavelengths, got it. Okay. So, this is the black body spectral radiance pattern. Okay. So, the Wiens displacement law was that by differentiating the Planck's formula with respect to lambda, he was able to find out the maximum. Okay. So, this is Wiens formula, okay, which expresses mathematically the common observation that colors vary from red to orange or yellow as the temperature of the thermal radiator increases, because the lambda at which the peak happens actually changes. The wavelength of the color is the same as the wavelength calculated for lambda max, got it. So, the wavelength of the color that it emits is the same as that, right. So, a good approximation of lambda max for a given black body temperature is applying the rule of thumb 3000 by T microns. Okay. So, if you know the temperature, okay, so 3000 by T will actually give you whatever is the lambda max. That means you would be able to see the color, whatever is the color corresponding to that you should be able to see. So, thus a very hot star such as Sirius, okay, which is 11,000 Kelvin, emits bluish white light, okay, radiates with a peak spectral radiant emittance which occurs within the invisible ultraviolet at about 0.27 microns. Sun, however, which is about 6,000 Kelvin, emits yellow light peaking around 0.5 micron in the middle of the visible light spectrum. Okay. The room temperature 300 Kelvin, okay, is the peak radiant emittance is about 9.7 microns. Okay. The room temperature, that is the 300 where we are sitting right now, is in the far infrared, whereas the temperature of liquid nitrogen, which is at 77 Kelvin, the maximum almost occurs at around 38 micron in the extreme infrared wavelengths. So, these are some of the interesting stats, right, that whenever the temperature changes, your peak wavelength changes, and you can see that at room temperature it is 9.7. Okay. Nitrogen, it is in the extreme infrared region, okay, whereas sun is in the middle of the visible, right, whereas star like Sirius it is about 0.27, which is in the ultraviolet. Okay. So, these are some of the stats that we give. Okay. So, the Planck curves, if it is plotted on a semi-log scale from 100 to 1000 Kelvin, the dotted line represents basically the locus, right, of the peak, okay, described by the Wiens displacement law. Okay. So, this is once again the spectral radiant emittance and the wavelength that we have plotted over here. Okay. So, these are interesting things, this is what we are going to use. Okay. Then you have the Stefan-Boltzmann law, which you must have read in your radiation heat transfer, that by integrating Planck's formula from 0 to infinity, we obtain the total radiant emittance of a black body, which is given by sigma T to the power of 4, where T to the power of 4 is the dependence. This is the Stefan-Boltzmann formula, okay, which states that the total emissive power of a black body is proportional to the fourth power of its absolute power, absolute temperature, right. Okay. So, graphically it represents the total area under the Planck's curve, because that is what you have indicated. Take any of this Planck's black body spectrum, you integrate it out, the total area under the curve is basically what we are writing over here. It can be shown that the radiant emittance in the interval from 0 to lambda max is only 25% of the total, which represents about the amount of sun's radiation which lies in the visible light spectrum. So, this is also another interesting fact, that from 0 to lambda max sun peaks around the visible, right. So, in that region you get only 25%, there is a long tail of the distribution. So, sun emits a lot of radiation in the infrared and higher up. Okay. So, using Stefan-Boltzmann formula to calculate the power radiated by a human body at 300, an external surface of approximately 2 meter square, we obtain it is about 1 kilowatt. Okay. Got it. So, these are some interesting facts, but this is an important thing, that the total emissive power that is emitted by a black body. Okay. But however, we have non-black body emitters mostly, right. So far only black body emitters and black body radiations have been discussed. However, your real objects never comply with these kind of laws. Okay. They might approach the black body behavior in certain intervals. For example, a certain type of white paint may appear perfectly white in visible white light, but become distinctly gray at 2 micron, and beyond 3 micron it is almost black, right. So, there are 3 processes which can occur that prevent a real object from acting as a black body. Okay. So, black body is very idealistic, it does not happen, okay. It does not exist. Okay. So, a fraction of the light that is incident radiation may be absorbed, let us call that alpha. A fraction called rho may be actually reflected, and a fraction tau may be transmitted. So, there are 3 mechanisms: absorption, reflectance, reflection and transmittance. Since all of these factors are more or less wavelength dependent, the subscript lambda is used to imply the spectral dependence of their definitions. So, the spectral absorptance, which is alpha into lambda, the ratio of spectral radiant power absorbed by an object to that incident upon it. The spectral reflectance is this rho into lambda, the ratio of the spectral radiant power reflected compared to the one that is incident upon it, and the spectral transmittance is basically whatever power is transmitted. So, you know the coefficient of all this, summation of all these things would be equal to 1, because it is a fraction. Okay. Has to be, because there is no other way the energy can go. For opaque materials, your transmittance is basically 0. So, you basically have absorbance or reflectance. Okay. The relation simplifies to something like this. Got it? Now, another factor which is called emissivity is required to describe the fraction of the radiant emittance of a black body produced by an object. So, we have the definition, the spectral emissivity is the ratio of the spectral radiant power to that from a black body at the same temperature and wavelength. Okay. So, basically you are comparing the black body with the real body. So, expressed mathematically, you are basically writing it as this divided by the black body. So, generally speaking, there are 3 types of radiation sources: a black body whose emissivity is equal to 1, a gray body whose emissivity is less than 1, and a selective radiator where this emissivity varies with the wavelength. There are all kinds, right. So, according to Kirchhoff's law, for any material with spectral emissivity and spectral absorptance are equal at any specified temperature and wavelength. So, basically this emissivity and absorptance are basically the same, okay, at any particular wavelength, right. For highly polished surface, this actually approaches 0. So, you have actually reflectance all the way. It is like a mirror, like a perfect mirror, that if you think about a mirror, that is exactly what it is. Okay. So, for a gray emitter, the Stefan-Boltzmann formula now becomes something like this. So, you now have the emissivity attached with it, right. So, this states that the total emissive power of a gray body is the same as a black body at the same temperature, reduced in proportion, okay, by that factor which is the emissivity, which is epsilon, right. So, you can see that one is basically the spectral, these are the two axes, okay. 2 is basically the wavelength, okay. 3 is basically the black body. So, this is our black body, okay. 4 is basically selective radiator. So, you can see that it varies with wavelength, and then the gray body, which is what we have done over here, is basically a scaled down version of the black body. Everywhere it is reduced by that particular factor with no selectivity with respect to wavelength. Okay. So, infrared semi-transparent material, now consider a non-metallic semi-transparent body, let us say in the form of a thick flat plate of plastic material. When the plate is heated, the radiation is generated within the volume. Moreover, when it arrives at the surface, some of it is reflected back. Okay. So, what happens is that the back reflected radiation is once again partially absorbed, some of it arrives at the other surface, some of it escapes. So, progressive reflections becomes weaker and weaker. They must be added when the total emittance of the plate is sought, right. So, when the resulting geometric series is summed, the effective emissivity of a semi-transparent plate is given by this particular form. We are not going through the math, but you can if you want, you can do it. Okay. So, here the plate becomes opaque when this formula reduces to something like this, right. Okay. So, the last relationship is particularly convenient because it is easier to measure reflectance than to measure emissivity directly. Okay. It is just a measurement wise, it is an easier way to do. Okay. So, the measurement formula, what IR cameras would normally use is that this is our camera, this is the camera which we would use to measure the temperature of any surface. That is what IR camera have been used, this is what we have been doing on the droplet surface, this is what we have been doing on the film cooling holes. So, when viewing an object, the camera receives radiation not only from the object itself, but also from the surroundings reflected via the object surface, right. So, it all contributions from all kinds. So, both these radiation contributions becomes attenuated to some extent by the atmosphere or by the measurement path, right. So, you can see all kinds of things that are happening, there is reflection, there is emission, there is all kinds of things which actually reaches the camera, right. Okay. So, what has been neglected, for instance, could be the sunlight scattered, okay, or stray radiation from an intense radiation source outside the field of view. Such disturbances are difficult. So, however, most cases they will be kind of small also, but if you are not sure, in your case you have to do a controlled experiment, that you have to do it in a controlled room environment, okay, where all these extraneous sunlights and other things are not there, right. So, assume that the received radiation power W from a black body source of temperature, okay, of T source on a short distance generates a camera output which is U source, that is proportional to the input power, right. This is U source, this is with respect to the input power. Okay. Should the source be a gray body with emittance, the received radiation would consequently be epsilon into W source, right. Now, we are ready to write 3 collected radiation power terms: emission from the body, right, which is epsilon tau W object, this is the emittance, this is the transmittance of the atmosphere, right. Okay. The object temperature is T object. Okay. Now, the reflected radiation from ambient sources is 1 minus epsilon tau W reflectance, where this part term is the reflectance of the object. Okay. The ambient sources have the temperature T reflect. Now, emission from the atmosphere, which is 1 minus tau into tau W ATM, where 1 minus tau is the emittance of the atmosphere, the temperature of the atmosphere is T ATM. So, the total radiation that is received is basically sum of this object, sum of this radiation, sum of the atmosphere, right. So, you have 3 terms basically, the total radiation that is the total power that it receives is basically a sum total of all these quantities. This is what the camera sees, right. Now, we multiply each term by the constant and replace the CW products by the corresponding U. So, your U total is somewhere like this, right. So, the U object is something like this, because you have to calculate the U object. Okay. So, the U object is the camera calculated camera output voltage for a black body temperature of T object. T U total is basically for the actual case. Okay. U reflectance is the theoretical camera output, okay, for a black body of temperature T reflectance, and U atmosphere is basically the theoretical camera output voltage for a black body of temperature T ATM according to the calibration. Now, the operator, whoever is working on the camera, has to supply the object emittance. That is why in IR camera you will see this term specifically appearing. You have to specify the relative humidity, you have to specify the temperature of the ambient, you have to describe the object distance, sometimes that is pre-done because you are focusing a camera. Okay. The effective temperature of the object surrounding, so the reflected surrounding temperature T reflectance. If you give all these terms, we can calculate what will be the temperature. Okay. So, once that is done, okay, once you are able to isolate what is the camera output voltage, okay, using these parameters, because you need to know the temperature, few things. Most of these things are readily available to you, because object emittance you can measure beforehand. Okay, the relative humidity is something that is already given, the T atmosphere is something that is known in the environment that you are working, and the object distance is something that is also known. So, the effective temperature, and combining all these terms, you can now come to a generalized expression in which you say that this will be my camera output voltage, and how is it actually related to the corresponding T source, right, T source or T object. Okay. So, that you should be able to now see, recalculate, okay, from this particular expressions. Okay. So, we have covered a long distance from black body to grey body, and how to calibrate, how to do the exercise, and then how to formulate the U source, and then ultimately it will give you a temperature. Other than that, it is just an emission signature. Okay. So, you have to convert that to a temperature through these methods. Okay. So, IR cameras can be fast, they can go up to about 300 FPS, it can be more in these days, they have a good spectral resolution, good spatial resolution as well, and they are very handy because they just depend on these radiation signatures to calculate the whole thing. Okay. So, here we have given you ideas about two systems, TLC and IR thermography. Obviously, these are bird eye views, and there are a lot of complications. Okay. It is not that simple, but this is just to give you an idea that how things can be measured, okay, and how things are practically measured, so that your computational models can be actually validated. Thank you. See you next class.